In this class, today's lecture, I will discuss about the fundamentals of electrochemistry, as the title shows. So, in this fundamentals of electrochemistry, I will be discussing about the basic concepts. Those points I just note down here. So, what about electrons? Because the branch of electrochemistry deals with the flow of electrons. We study the nature of the flow of the electrons and about the electrodes. Then comes the electrolyte. So these are the two main components of an electrochemical cell. So this comprises of electrochemical cell. So these are the basic topics which I'll discuss today. So let us come to our first question which I put: why electron flows? So electron flows when there is a potential difference. That thing you have to understand, that when there is a potential difference. So let us consider a high potential, suppose negative to positive. Now we have an electron somewhere. So this electron, which direction it will flow? It will flow from negative to towards the positive. So this is high potential with respect to the electron, high potential. This is the low potential. That is the determinator for the electron to flow. Now, how to show this in a material? So for that, we have to consider the energy diagram. So this same thing I discuss in energy diagram, where this is my energy. Now I am taking example of two electrodes, that is zinc electrode and copper electrode. So my copper energy is here. Now why it is here, I'll just explain. Let me write down here. So now I have taken two materials, that is one zinc, another copper. And this zinc is a positive electrode, as you may know, and copper is a lesser positive than zinc. So you may consider here negative. So why electron will flow, which will be the determinator for the flow of the electron? That is the Fermi level. So Fermi energy level is the determinator. Fermi energy level. So this is the energy diagram. So you can understand by using the energy diagram. Now here, in case of zinc metal, the Fermi energy level, that is the highest occupied molecular orbital or energy level for, that is the zinc. And this Fermi energy level for zinc is higher, as you see in the diagram, compared to copper. So these are the Fermi level, that is the highest occupied. So there are many energy levels here below this you can have, but this is the highest energy level. So this is the limit that it can hold. So when you connect this to an external circuit, the electron will flow. How it will flow? From zinc to copper. So how long this electron will flow? That will be determined by the energy. So this energy. So that energy difference, if I write, this energy difference is known as free energy, delta G. It is known as delta G. What is delta G? The Gibbs energy or free energy. Now this is mathematically related as delta G equal to minus NFE. So delta G equal to minus NFE. Now how long this electron will flow depends on this parameter delta G. So as you initially find, our delta G is negative here. So this negative here determines the flow of electron is spontaneous. So it shows that the flow of electron is spontaneous. Now how long it will be spontaneous? And slowly as we go on, this zinc level will come here around and copper level, because copper is getting filled up with electrons. So copper level will be coming on the above. Slowly it will increase, and zinc Fermi energy level will decrease because electrons are getting lost from zinc. So this determinator of delta G minus means delta G negative means delta G, when it is negative, means it is spontaneous. This you have to remember. Now how long this will flow? And delta G becomes 0. So at this level here, my delta G becomes 0. So this is known as equilibrium. So this is equilibrium, or in terms of electrochemistry, we say the cell is discharged. So this zinc and copper has formed a electrochemical cell, we can say. And here it shows how long this electron will flow until the delta G becomes 0. So this is known as discharge of a cell, this condition. In terms of electrochemistry, discharge of the cell. I hope is this clear. I'll again repeat. The flow of electron will be from the electropositive metal to the electronegative metal, and electropositive metal is that metal which has high Fermi energy level. Now what is potential? Because here is a difference in potential. As I told, high potential to low potential. So this is my high potential, this is my low potential. So you can say in terms of this, zinc is at high potential and copper is at low potential. And how long this flows? When the two potential becomes equal, and that is equilibrium condition. Now what is potential? I'll just define. So potential at a point, you can say potential at a point is the work. It is the work done. You can say potential is the work done. Now what is this type of work? This is simply electrical work, and that electrical work is this free energy difference. So this electrical work which you are getting, IWLEC, is nothing but the free energy change. So this electrical work is free energy change, and as I have related here, N is the number of electrons per mole involved in this process, F is the Faraday, and E is the electrode potential. So minus NFE. Now it is the work. So as we see, it is the electrical work. Okay, so it is a non-mechanical work, we can say, in terms of thermodynamics. It is a non-mechanical work, and that is related to the free energy change of the system. So it's equals minus NFE. Now this work done, potential, if we define fundamental definition is the work done. Suppose I want to know the potential at a point, this. So how much is the potential? This is an electric field, this is a huge electric field. I want to know the potential at a point. So definition of potential is the amount of work done to bring a unit charge. So maybe I am bringing an electron which has a unit charge from infinite distance to that point. So suppose here. So when you bring this work done is my potential, and that is my electrical work, and which equates minus NFE. If I am bringing more electrons, so N comes, otherwise this is only Fe. So if I say, for example, my potential here is 2 volt. If I say potential is 2 volt. So what do you mean by the statement? It means the amount of work will be 2 volts is bringing this unit charge is 1 into twice a volt. So this is 2 joules. This is coulombs. See, I am writing. So 1 coulomb of charge and unit charge, that is 2 volts. So 2 joules of work is done. If we say potential at a point is 2 volts, that is to bring a unit charge from infinity to that point, we need this much work is done, 2 joules. I hope this is understandable. Then I will move on to the next part. So our next part is about the electrons. So what is an electrode? As we have seen here, the electrode means the conductor which allows flow of electrons. So electrodes are conductors which are electronic conductors, you can say. So electrode you can define as the materials which conduct electrons, which conducts electricity through electrons. So material which conducts through electrons. This is the fundamental definition of electrodes. They are purely electronic conductor, you can say. So example, Generally metals like copper, zinc, platinum, etc. They are purely electric conductors. And what about electrolytes? Electrolytes are materials which conducts through ions. Conducts through ions. So they are mainly conduct materials which conduct through ions. So example is salts, acids, gases. Okay? These are the type of substances which conduct through ions. Now these electrolytes have been differentiated into two types. So they are strong electrolyte and weak electrolyte. I'll just write it. So strong and weak. As you see, strong electrolyte and weak electrolyte. So what is a strong electrolyte? Strong electrolyte are materials or substances, we can say, which dissociates almost completely. So here we have example of, it can be a acid, it can be a base, it can be a salt. So strong electrolytes dissociates almost completely. So example of acid, I'll write one example, sulfuric acid you can say, as well as hydrochloric acid. So they dissociates almost completely into ions. An example of a base which dissociates almost completely, I can write as potassium hydroxide. These are the example of a strong electrolyte. It dissociates completely into, almost completely into ions, that is potassium ion and hydroxyl ion. Similarly, salt I can write as Na2NaCl. So sodium chloride is a salt which dissociates almost completely. It dissociates into sodium ion and chloride ion. Let us come to the weak electrolytes. So here also we have acid and some base. So what is a weak electrolyte? It is just opposite of the strong electrolytes. So electrolytes which dissociates all partially or incompletely. So electrolytes which dissociates partially or incompletely are known as weak electrolytes. So example of an acid which is a weak electrolyte is your acetic acid. So this acetic acid dissociates incompletely or partially. Its dissociation constant is very low. An example of a base which dissociates almost incompletely is ammonium hydroxide, or ammonia, you can say aqueous solution ammonia. So I gave one example for each. So electrolytes are ionic conductors, and we have strong and weak electrolytes. In strong electrolytes, we have strong acids, strong base, salts, and weak electrolytes, we have strong acid, weak acid, and weak base. So I hope these examples are clear. Now, two basic components we understood here about the electrode and the electrolytes. Now, if we combine them, our main aim in electrochemistry is to get some electricity from chemical reactions. So the chemical reactions are redox reactions, or reactions which involves flow of electrons. So this next part is how you are combining this to form a electrochemical cell. So now this part I will concentrate on electrochemical cells. So how to define electrochemical cell? First you have to define it. So how will you define electrochemical cell? As we seen, the electrochemical cell basic components are electrodes and electrolyte. So we understood the definition of electrodes. Electrodes are electronic conductor. Electrodes are electrolytes are ionic conductor. Now when you combine them, we form the electrochemical cell. So how to combine them? It is like forming a sandwich. As you know, sandwich, we have two breads, in between we have some stuff. Okay, so you compare this as a electrochemical cell. So here the breads in the sandwich are electrodes. So I can show you the schematic. So this is my electrode, and these are the two electrodes. I require two electrodes, and in between I have a electrolyte. So I'm showing with red is electrolyte. So definition of electrochemical cell can be told as a ionic conductor. Now this is an ionic conductor, the electrolyte, ionic conductor. This is being enclosed by electronic conductors. This is also an electronic conductor. So two electronic conductors are enclosing an ionic conductor. So you can consider the electrochemical cell as the ionic conductor enclosed between two electronic conductors. Now this nature of the electronic conductors will be based on their Fermi level. You have to choose the electrodes, that is the electronic conductor, which have a difference in the Fermi level. We cannot choose the same material. So there has to be flow of electrons. So how the electron will flow? Until unless we have a difference in the Fermi energy level. So this, to know this, we have a more electrochemistry has given benefit because already much work has been done with us. So we check the electrochemical series. So according to electrochemical series, we can get the proper electrodes, because in the electrochemical series we have the negative charge electrodes at the top and the lower charge electrode at the bottom. It is like, and hydrogen is at the middle. So this is how the electrodes material can be obtained, and how to form the cell will be determined by this E, the difference, that EMF of the cell, which will come. So suppose now this is my zinc and this is my copper, as we have shown. So in the electrochemical cell, we connect two materials which have difference in Fermi level. So my left hand side electrode, this is known as LHE and this is known as RHE. So for an electrochemical cell, what it does, the electrochemical cell, it converts chemical energy into electrical energy. And generally, this electrolyte is taken as, in the zinc side, zinc sulfate, and in the copper side, copper sulfate. So these are the electrolytes. And it has to be connected with a salt bridge. So if I draw a more specific diagram, this is my zinc electrode, this is my copper electrode, this is zinc, this is copper, and my electrolyte is here. It has to be made half because salt bridge will come. So this is my, so this is enclosed in zinc sulfate, ZnSO4, and this is enclosed in copper sulfate, CuSO4. These are connected through a salt bridge. So this is my salt bridge. Again, I repeat. So this is my copper electrode dipped in copper sulfate. This is zinc electrode dipped in zinc sulfate, and it is connected through an external circuit. These two electrodes are connected through an external circuit with a resistor. So it may be written as a resistor, which is withdrawing the load. So this is how the electrochemical cell looks. So this is example of Daniel cell. This was made by Daniel. This is termed as Daniel cell, where zinc is dipped in zinc sulfate, copper is dipped in copper sulfate. You connect it through a KCl agar-agar salt bridge. So here to the external circuit, you get flow of electrons. So now how this is working, because we have left hand side, you are keeping zinc electrode, which is electropositive, and right hand side, you are keeping copper electrode, which is less electropositive than zinc. So electrons will flow from zinc to copper through the external circuit. And within the internal circuit, electrochemical reaction will start. So my left hand electrode, that is my cathode here. So LAG, I'll write here LAG, that is my cathode, sorry, anode, because it is oxidizing. Again, I repeat, my left hand side is the anode because it is oxidizing. Electron is lost from zinc to zinc sulfate. So the anodic reaction is Zn is losing electron to Zn2 plus 2e, and your cathode or right hand side electrode RHE is my cathode. So where copper 2 plus, it's from copper sulfate to, it is gaining 2 electrons lost this, and it is forming copper. So this is how the net reaction is Zn plus Cu2 plus gives rise to Zn2 plus plus Cu. So this is the overall reaction which we get from the Daniell cell. And how long these reactions will give me the flow of electrons to the external circuit? Until unless the delta G becomes 0. So at delta G becomes 0, there will be no flow of electrons. So again I repeat, the zinc is dissolving as zinc 2 plus, and copper 2 plus gets reduced on the copper electrode. That is, deposition of copper you will find on the copper electrode, and dissolution of zinc you will observe when the Daniell cell runs. When at equilibrium, the delta G will become 0 and the cell reaction will stop. So you say the cell is completely discharged. So this is a primitive example of the electrochemical cell. So which we got from two electronic conductors have been kept in between an ionic conductor. Now in the next part, we'll discuss about the potentials. This potential of the electrode. So what is electrode potential? That is the next part of our discussion. So electrode potential. What is this term? Because we are more interested in potential. Because of potential, we are getting this electron flow. So what is electrode potential? So electrode potential is the tendency. So if you take a electrode, that is a metal, I write it as M, and you keep it in contact with the electrolyte. I'm showing the electrolyte. And in blue I am writing, this is my electrolyte, and this electrolyte contains Mn plus. So the metal and its salt, which is in contact with each other. So at the electrode electrolyte interface, what is happening? That is that electron transfer. So when this metal, suppose the electrochemical reaction is like this, Mn plus plus Ne giving rise to M. So this is a reduction reaction. So reduction. So reduction is happening. Metal ion is accepting electrons and getting to the zero oxidation state. That means it is deposited here. So when a metal electrode is in contact with its electrolyte, and this is the electrochemical reaction happening. So this is a reduction. So the tendency of a metal to gain or loss. So here it is gaining electron. So electrode potential means the tendency of an electrode to gain or lose electron when it is contact with an electrolyte. So this is half cell, we are seeing half cell potential. So this is reduction potential. So this is denoted as E naught when it is in standard state. Standard state means at 25 degrees centigrade and at 1 atmosphere pressure. So then it becomes E naught. When it is at any temperature, we say it is E. So that is the notation for electrode potential, and E naught means standard electrode potential. So I'll write in terms of standard electrode potential. So some value we'll get, unit is volt. So this will be generally negative. The reduction potential generally negative will find. It can be positive also. Okay. So depends on the, so it may be positive or it can be negative. I'm writing plus or minus. Okay. So again I repeat, the potential, the electrode potential is the tendency of electron to lose to gain or lose electron when it is in contact with an electrolyte. So we denote it as, more properly, E0. This reaction potential is denoted as Mn plus this couple M. So then we term it as reduction potential, or more properly as I written E naught. So it is standard reduction potential. That means it is the electrode I have kept in standard state. So standard reduction potential. Similarly, I can denote as oxidation potential, but generally by convention we report in terms of reduction potential. So oxidation potential, if I write for the same electrode, it will be M from Mn plus. We are getting M, this is reduction. So M to Mn plus means the opposite reaction. So this is my reduction, top RED I'm writing, and this will be my oxidation, OX I wrote. So forward reaction is reduction, backward reaction is oxidation. So the couple will be written like this. An opposite reaction is happening. This is my standard oxidation potential, I can say. But according to convention, we report in standard reduction potential. I hope this is clear. The unit of standard is reaction potential or reduction potential is in volts. As the definition shows, it is the work done, and this is related to, the work done will be related as minus NFE. So whatever E we are getting, you have to multiply with number of electrons, but here it is N electrons. So N, and F is the Faraday, the charge accompanied with the each electron. So this is the broadly how to define the electrode potential, that is electrode electrolyte interface, the phenomena is happening. Now this is a single electrode. Now when you combine this, we get the full cell. So how to denote that net cell EMF? So cell EMF is written as right hand side, your right hand side electrode EMF minus the left hand side electrode EMF. This is how the cell EMF is reported. RHE, LHE means RHE minus LHE. So this is my cathode. This is my anode. So this is my E cell. So this is how the cell is cell EMF, net cell EMF is represented for any electrochemical full cell, that is. So this is how I have explained. So let us again a little bit summarize it up. So why electron flows? Electron flows because of Fermi level difference. So from higher Fermi level to lower Fermi level, the electrons will flow. And what type of material you will choose? That is the electrodes. You have to choose based on this Fermi level. That is a determinator. And you need a medium. Now, question may arise that without electrolyte, can you run a cell? So the answer is that if we don't put an electrolyte, we will get the short circuit, we say generally. So two electronic conductors, if we put together, it may not give any output. So we need a medium because this electrochemical reaction has to happen. So the electrodes are electronic conductor and the electrolyte is ionic conductor. So here the electron ionic, that transformation should happen. Electrons should flow to the electrode, to the electrolyte, and electrolyte from the ions will give the electron back to the electrode. So this oxidation reduction process occurs at the interface. So this is the region where the reaction occurs, and that is called the double layer region. That electrode electrolyte interface region is known as the double layer region. So they are in this, and this is angstrom thickness. Angstrom. So this thickness of the double layer is the angstrom thickness where this phenomena happens. So it is a very small region. We cannot notice with our eyes. So very small region, that is angstrom thickness, where the electron that is transfer of electron occurs from the electrode and the electrolyte. And how to determine the cell EMF is this following thing. And when you combine these two, so this cell EMF should be positive. So this E should be positive to get a cell output. That is, for to get spontaneity in the cell, we require this. Now, what are the different types of electrochemical cell? So there are two types of electrochemical cell, that is galvanic cell and electrolytic cell. Electrochemical cell are of two types. We have galvanic cell and electrolytic cell. So this is galvanic cell. I have written left hand side. This is electrolytic cell. Now, what is galvanic cell? The galvanic cell, what we have, same electrochemical reactions are occurring, but here the chemical energy is converted into electrical energy. So example is that Daniel cell which I put NiEl. And this example is, you can take Kastner cell. So here you get the opposite. Again, I repeat, Daniel cell means chemical reaction is chemical energy is converted to electrical energy. Example, Daniel cell. And here in the electrolytic cell, we have to pass electricity to get the chemical. Okay. So example is sodium electrodeposition, which is happening in a Kastner cell. It deposits sodium from sodium chloride, molten sodium chloride. So we get the chemical means reaction by applying electricity in this electrolytic cell. So galvanic cell, we get electricity from chemical reaction, as we saw, dissolution of zinc and deposition of copper in a zinc copper electrolyte and zinc sulfate copper sulfate electrolytic system. So that is my Daniel cell is one of the example. You have these dry cells also, Lakeland cell. These are the examples of galvanic cell. So this are useful for our application towards battery. Okay, and this is mainly for electro refining purpose. So these electrochemical cell are for electrometallurgy purpose. You can define electrometallurgy, that means extraction of metals. This we apply for our battery, or mainly battery and fuel cell. One example you can put. So fuel cell battery application, we require this concept of galvanic cell. And for electrometallurgy concept, that is extraction of metal, is based on this concept of electrolytic cell, extraction of metals. This gives you high pure metals, 99 point is 99 plus purity. We get these metals through electrolytic cell. So we'll discuss more on this galvanic cell. So first we'll discuss about the electrochemical reaction, which we have already stated. So here cathode means reduction occurs, reduction reaction, and anode means oxidation reaction will happen, oxidation. So these are my electrodes in a galvanic cell. These are my electrodes. So which on the cathode we have reduction, on the anode we have oxidation, and the electrolyte, we need an electrolyte also. So this is simply a ionic conductor. And for this, When you combine this, we get a free energy difference, that is negative. Is delta G. When you combine, it becomes negative. So then only the reaction happens. We say the cell is spontaneous. So spontaneous on its own, it will run. So this cell will be spontaneous. We say the cell is spontaneous. So as long as this delta G is negative, it will give flow of electricity through the external circuit. And when it becomes zero, it will stop. And but what is the nature of here? If you see, the electrodes are similarly, we need electronic conductor, same electrodes. Electrolyte should be ionic conductor, and the electrolyte we are choosing for the extraction of the metal here based on the nature. Suppose sodium extraction means we'll use molten NaCl. So here our this electrolyte is chosen which metal we want to extract. So example, molten NaCl for this caster cell we want to get. So this electrolyte is this molten NaCl, and it is the ionic conductor, and here the delta G is positive. For this, when you combine the cell, we take two electrodes. Suppose I'll write cathode and anode are more or less same. Cathode is graphite, anode also we take graphite. Because high temperature cell, it is done at 800 to 900 degrees centigrade. So these are mainly done in inert atmosphere. So high temperature resistance graphite electrodes are used, and the delta G for the process is positive. Hence, we are passing external electricity to the external supply. So through external circuit, we pass electricity in this electrolytic cell, and the electrolyte gets decomposed. So sodium is deposited at the cathode, and oxygen or chlorine is evolved at the anode. So this is how our electrolytic cell occurs. Our electrolytic cell involves the following electrochemical reactions. So this is for commercial metallurgy purpose, and this is for our electricity need, galvanic cell. So the name Galvani came from Galvani, the scientist, Italian scientist who developed this. So this Galvani potential, he found this galvanic potential. He found out the galvanic potential, that electrode electrolyte interface potential. Based on this, these electrochemical reactions are happening. So under his name, this galvanic cell has been put. So I hope I have made it clear. These are the fundamental concepts. So about the electrodes, electrolyte, electrochemical series, and how to combine these electrodes, what is the way to combine. So based on the Fermi energy level, then we have two types of electrochemical cell, that is galvanic cell and our electrolytic cell. So what is the basic difference between this? And another thing is the nature, is charge of the electrode. For this galvanic cell, this cathode is taken as positive and the anode is taken as negative. This should be remembered. So cathode is positive charge for a galvanic cell, anode is negative charge. For a electrolytic cell, the sign only changes. Cathode is negative and the anode is positive. This is how you determine. So only difference is positive is the cathode charge in galvanic cell, and in electrolytic cell, negative is the charge of the anode. So this cathode means electron reduction will occur, that is gain of electron, and anode means oxidation will occur, that is loss of electron, and the sign only changes. So this is the difference between galvanic cell and electrolytic cell. Their difference in their operation, that is galvanic cell produces gives electricity, so chemical energy from chemical reactions, and electrolytic cell is splitting, means chemical through electric passage of electric current, we get the chemical reaction happens. And the difference is the nature of the difference of the electrode. So I hope that I have more or less defined out the fundamental concepts, why we need electrochemical cells and how to form a electrochemical cell. So I hope this lecture is useful for the beginners in electrochemistry. So thank you.